Hello friends, in this video I'd like to solve the following problem from the Irish Mathematical Olympiad 1993, problem number 8. We want to prove that if 1 is less than or equal m and m is less than or equal n, and if they are integers, then the following sum from k equals 1 to infinity of n minus m plus 1 choose k times m minus 1 choose k minus 1 equals n choose m. My hints for this problem. First of all, although our series, our sum goes to infinity, only finitely many terms are non-zero. Because think about the basic property of binomial coefficient. It says in how many ways can we choose k elements, k things, from the collection of n minus m plus 1 things. If k is greater than the upper index, there is 0 ways to do it. So our symbol, our binomial coefficient goes to 0. Moreover, r choose k equals r choose r minus k for integers 0, k, and r, satisfying this inequality. And finally, the most crucial part is so-called Vandermonde's convolution or Vandermonde's identity, which says that if we have three non-negative integers, n, r, and s, then sum as k goes from 0 to n of r choose k, s choose n minus k, this entire sum can be simplified to r plus s choose n. You can look up this identity on Wikipedia. The proof is quite simple. Okay, so give this problem a try and I will see you in a moment. Okay, so first of all, my solution will be as follows. First of all, let's consider our sum. It is that sum. And notice that n minus m plus 1 choose k is 0 if k is greater than n minus m plus 1, and similarly, m minus 1 choose k minus 1 is also 0 if k is greater than m. So, in fact, our sum, it suffices to sum from k equals 1 to the minimum of these two numbers. To the minimum of n minus m k plus 1 comma m of our expression. Okay, that's nice. And now we will consider separately two cases, because we need to find this minimum. So either this minimum can be this number or that number. Case number one, n minus m plus 1 is greater than or equal m. Then, for the brevity's sake, let's call that this sum s. Then our sum s goes from k equals 1 to m, n minus m plus 1 choose k, and here, the second part, I will use the fact that there is some kind of symmetry going on with binomial coefficients, namely, m minus 1 choose k is the same as m minus 1 choose m minus 1 minus k minus 1. And now, this entire sum is the sum as k goes from 1 to m, n minus m plus 1 choose k, choose m minus 1 times m minus 1 choose m minus k. Very well. We'll put it maybe a little bit further. Okay. And now, let's notice there we have a perfect setup for Vandermonde's identity. And exactly by Vandermonde's identity, this entire sum is the sum of the upper indices over m. And it's obviously, after simplification, n choose m. So we have proven our theorem in this case. And second case will be very similar. Case number 2, when n minus m plus 1 is strictly less than m, let's say, then our sum runs from k equals 1. Now it will go only to n minus m plus 1 of n minus m plus 1 choose k, m minus 1 choose k minus 1. Okay, and now maybe in this step, I don't want to write too many things. Now, in a similar manner, I can change this first binomial coefficient. It's the same as n minus m plus 1 choose n minus m plus 1 minus k. Okay, and now again, we have a perfect setup for our Vandermonde identity. We just add upper indices over this sum oh no, one more thing. Yes, one more thing before we go. We need to change we need to move our index of summation to be able to use Vandermonde identity. So instead of k, let's put in every place k plus 1. So if k goes from 1 to this number, k plus 1 goes from 0 to this number. We have n minus m plus 1. And here we have, after changing k to k plus 1, we have n minus m minus k. And here we have m minus 1 choose k. And now we can use Vandermonde identity. And now we know that this entire sum is n minus m plus 1 plus m minus 1 over choose n minus m. Simply choose n minus m. Let's write it in the middle. And that is n choose n minus m. And n choose n minus m by symmetry, it's n choose n minus m, and that's just n choose m, which closes our proof and closes our video. So as you can see, Vandermonde identity can be very useful when dealing with sums of binomial coefficients. Thank you for watching and see you next time. Goodbye.